All right, folks, this is chapter 3-2. This is recording number 4. Okay, so we left off here talking about this so-called coefficient of variation. And the concept is, I think, very straightforward. The formula might be something that, like, where did that come from? But that's a little bit beyond the scope of this book, or excuse me, the scope of this class to prove or to derive various measures that we use. This is an elementary statistics, so we just kind of accept these things as being true. Okay. All right. So what's the concept? The concept is that if you have 2 samples or 3 samples or 4 samples, however many you have, if you have all these different samples, you can calculate the variance and the standard deviation for each of those samples, right? Easy to do. We have the formula. Okay. Moreover, we can compare the standard deviation and the variance of those 3 or 4 or 5 samples, right? If, but only if, they're the same units of measurement. Okay, now, so let's think about that. Let's suppose we have all these kids in the class or in the school district, okay, and we take 5 samples and we are measuring something or another, whatever it happens to be, grade point average, IQ, how much they weigh, what their age is, whatever it is that we're measuring. Okay, if we're comparing the same units of measurement, the same thing, whatever it is, then it makes sense, right? We can compare sample 1 to sample 2. We can compare sample 1 to sample 3, and so forth. That's if and only if they're the same units. But there will be occasions when we are not interested in comparing the same units. There will be occasions when we want to compare different units. So that's what the coefficient of variation is used for. So here's the example the book uses. The book talks about an automobile dealer wants to compare standard deviation of miles driven for the cars, and we're going to look at standard deviation for Buicks, and we're going to look at the standard deviation for Cadillacs. Now, obviously, nobody cares about this in real life, right? You don't care about it. I don't care about it. This is just an example, okay? This could just as easily be the standard deviation of pulse rates, and you're trying to get some sort of a medication approved by the Food and Drug Administration, okay? So the concept is what counts here, so don't be put off by these stupid examples. Okay, so it makes sense, right? The standard deviation for Buicks can be compared to the standard deviation of Cadillacs if we're talking about miles, okay? All right, so easy enough. On the other hand, let's suppose you want to compare something else. You want to look at what's the standard deviation of 2 different variables, the number of sales per salesperson compared to the commissions made by these persons, okay? Well, they're different, right? I mean, on the one hand, you're talking about the number of sales. On the other hand, we're talking about commissions. So we're talking about a number of sales compared to dollar commissions made by these salespeople. So if we want to make that kind of a comparison for whatever reason, then what we use is a different measure. It's a statistic. It's not a parameter. It's a statistic because it is comparing samples, and we call this the coefficient of variation. Coefficient is a kind of a generic term. We use it all the time in mathematics. It just basically means a number. It is like a coefficient of, in I don't know, like in my old business, working on the missile program, we would have what was called the coefficient of drag, and that would be as some sort of a vehicle is going through the atmosphere, how much drag does it have? That's based on the shape of the it's based on the shape of the vehicle. It's based on the density of the atmosphere, things of that sort. Okay, but it's just a number. So here we go. CVAR, that's the abbreviation he's using. That's the standard deviation, and it's divided by the mean. Okay, so it's S divided by X bar. Okay, and that's for samples, and then for populations, it's sigma divided by mu. Now, isn't that interesting? I should have read ahead a little bit. He says here a statistic that lets you do this. Okay, but then he's talking about populations. So, obviously I could rewind this video and not look so stupid, but I want you to know that I'm stupid sometimes. And I misread that. I don't know why the author says a statistic. It's a, because normally we use the word statistic to mean an attribute or a characteristic relating to samples, and we use the word parameter when we're talking about populations. So I don't know why he calls it a statistic. That's really not right as far as I can tell. In any event, let's just call it a measure that we can use. We have them for samples and we have them for populations, okay? All right, so let's take a look at this. We've got the sales of automobiles, okay? And we've got two different things here. We got the mean of the number of sales, and we have the mean of the commissions, okay? So we just plug into the formula, and what do we come up with? We come up with 5.7%, 14.8%, okay? And apparently, at least this author, the way he wants to do it is he wants to have it in terms of of percentages. If you, by multiplying it by 100, you multiply, see, 5/87. That's the formula. S divided by X bar. That comes out to be 0.0574712 according to my calculator. Okay, but what this author wants to do is let's multiply that by 100. That puts it into terms of percentages, so that's 5.7%. And that's okay. Other authors might not do it exactly that way, but that's perfectly okay. It doesn't matter, right? I mean, in other words, 5.7% is the same as 0.057, and that's what we get approximately if we have 5 divided by 87. Okay, so the punchline of this is what he says right here. The coefficient of variation is larger for commissions. So he has 14.8%. Or you could say it's 0.148. I mean, you know, no matter how you slice it, it's still baloney, right? So if you whether you multiply by 100 and get a percentage, or whether you leave it as a decimal, it doesn't make a bit of difference. In any event, the coefficient for variation is larger for commissions. So what we say then is that commissions are more variable than sales are, okay? So that might be something you are interested in. All right, so here's another one talking about roller coasters. We're talking about different types of roller coasters, whether they're wooden. Hold on one second. Okay, strike that. We're talking about the characteristic of interest that we are concerned with is height compared to speed. Okay, so we're talking about the speed and we're talking about the height, and we want to know, which is more variable. All right, so we do the calculation and we say, well, the variation of speeds is slightly larger number than the variation in heights. So we say that speeds is more variable than the height is. Okay. All right, so now let's change the subject. This is now a new topic, range rule of thumb. This is just an approximation. It's handy to have. It's called the range rule of thumb, and it's a rough estimate. A rough estimate of the range is the following. I may have said that wrong. It's a rough estimate of the standard deviation. The standard deviation is this little symbol right here. That means approximately equal to. So the standard deviation is approximately equal to the range divided by 4. Now this is also an approximation for the range, right? I mean, if you didn't know the range, you'd say, well, the range is equal to approximately 4 times S, right? Just do the arithmetic, multiply both sides by 4, and range would be approximately equal to 4 times S, okay? So it's an approximate value. Now, obviously, if there are these really big outliers, this is not a very good approximation. So you have to use a little bit of common sense. That's where your judgment comes in, okay? All right, so I'll let you read that, okay? Okay, then this next concept here is kind of using the same idea that we can make these approximations. Now, in order for this to make any sense, these distributions have to be reasonably well behaved. You cannot have these ridiculous outliers, using my example before of Bill Gates walking into the room. If you have something like that, then these approximations are not any good. Okay, so you can talk about the largest and smallest data value. The smallest data value will be approximately 2 standard deviations below the mean, and the largest will be approximately 2 standard deviations above the mean of the data set. Okay, so if I just give you the x bar and I give you the standard deviation, you can approximately tell me what the largest data value is and what the smallest data value is. Okay, and so as he says here, you can get a better approximation by using what is commonly referred to as Chebychevs Theorem and the empirical rule. These are two separate rules, two separate concepts, okay? And then we're going to explain those next here. All right, I think I have time to do Chebychevs Theorem. Okay, so Chebychevs Theorem is a way of telling me how much of the data is within a certain standard deviation of the mean. Okay, and it's to determine the spread, otherwise known as the dispersion of a variable. The different, the words basically mean the same thing. How much are you spread apart? What's the dispersion? How far are you away from x bar, or the mean? Okay, so this all makes sense, right? Because I've said before that the standard deviation and the variance is a way of describing how spread out things are. Okay, and as we've already discussed, the larger the variation is, or the standard deviation, they're Tweedledee, Tweedledum, right? And if you don't know what that means, Google it. The variance, or the standard deviation, let's say, the standard deviation is the square root of the variance, right? So if you know one, you know the other. The variance is just the mean of the square of the deviations. So it kind of makes sense that whenever we're talking about variance and standard deviation, what we're basically doing is we're coming up with a way of describing how spread out things are, okay? And we're going to have some cartoons here in just a minute that will help illustrate this. So if two variables that are measured in the same units, have the same means, let's say 70, the first variable has a standard deviation of 1.5, the second one has a standard deviation of 10. Well, what can you say? Well, you can say on average, the values are the same. I mean, it's like the paint we used before. The mean is the same for the two different variables. But the data for the second variable is more spread out than the data for the first variable. Okay, so now I'm going to get down in the weeds here. Okay, I'm going to really get some nuances here. I hope you don't mind, but I promised I'd try to help you read a math book and add some value here. I don't like the way he says this. Okay, it's confusing and it's a little bit misleading. He's talking about two variables. So let's suppose the two variables, measured in the same units. I mean, let's say temperature, 70 degrees temperature in Fahrenheit, okay? All right. It's not the variables that you're looking at that have the two different standard deviations. It might be like the months, or it might be the locations, let's say Riverside and Redlands have the same mean, 70 degrees temperature in the month of March, okay? All right. Well, they're not two different variables, right? So I don't know why he uses the word two variables here. What he's really talking about is two different data sets. He's talking about two different distributions. What he's really saying here is, hey, if Riverside has a mean of 70, if Redlands has a mean of 70 degrees, okay, but Riverside has a standard deviation of 1.5 and Redlands has a standard deviation of 10, then the data for the distribution for Redlands is more spread out than the distribution for Riverside is. That's what he's saying there. I don't know why he's using the word variable here. To me, that's just not right. So anyway, I hope that added some value. Let me end this video, and then we'll talk about Chebychevs theorem in the next video.